Hey everyone, here's a video on quantum mechanical model of the atom and especially orbital shapes, which will set us up for electron configuration next week. So let's take a look. The quantum mechanical model of the atom treats electrons like a wave and a particle. So the big issue is we can't really talk about a specific location for the electron anymore, only a region of space where it is most of the time. So this complicates things a little bit because we can't find a path or an orbit or anything like that. So electrons are a wave of quantized energy. So they're both wave, that's the wave part, and a particle, which is the quantized energy part. So they're complicated. They're both at the same time. They have properties of both, and that makes things tricky. So instead of talking about where they are specifically, we talk about them in orbitals, regions of probability. So we say here's a zone in which you can find the electron 90% of the time. And that actually gives us a well-defined zone, and we can talk about the shapes of those orbitals and which electrons are in them and how many. So the orbital is the region of space. An orbit is a pathway, but an orbital is a region of space where this thing is going to be most of the time. Now, these orbitals have different shapes. So you might think of them all as a sphere or some kind of Jimmy Neutron thing, but they actually each have their own unique shape. So an s orbital is a sphere shape. You can picture the nucleus right there in the middle. And then here in the middle of all the vertices would be the nucleus. And then we have this p orbital shape, which there are 3 of. They just point differently in space. Some of them point vertically, horizontally, and others front to back. And so 2 electrons will fit in each of these shapes, no matter what their shape. So notice that there's just one kind of s orbital. There are 3 p orbitals. And then if we look at the d orbitals, there's actually 5 of those. And the last one looks a little silly, but to an electron, they actually look identical. If you ask an electron, hey, find the d orbital that's different, it'll be like, what are you talking about? They're all the same. So notice the pattern goes 1, 3, 5. So if we were to have the next orbital, and I tell you that it was an f orbital, you would rightly guess that it has 7 orbital shapes. So 1, 3, 5, 7. You should know that the s orbital is a sphere. You should know that p orbitals are, they kind of look like a bow tie, but everybody in science calls them a dumbbell, like a little hand weight. So we're going to call it a dumbbell. And then the d orbitals are more like a clover leaf. So know those names, and the other ones you don't really need to know. This shows the periodic table and what kinds of orbitals are in each zone on the periodic table. This will be important next week when we talk about how to do electron configuration. But just know that there are different spots on the table for different shapes. If you look at this column here, you can see that a 1s orbital and a 2s orbital, they're really the same shape. They're all spheres, but as you go to lower and lower rows on the table, which would be higher and higher energy levels, what's happening is the orbitals are getting bigger and bigger. So this little blue zone inside here is actually this 1s orbital. And so you can see that they're the same shape, they're just larger and larger. So again, here are the 3 shapes you need to know, S, P, D. Now the energy level is what we talked about with the Bohr model. So if you think of those rings again, those are your energy level. The sublevel is the shape. So you just have to remember when you hear someone say sublevel, it means shape. On the test, you're going to look and be like, what are you talking about sublevel? So just remember sublevel is shape. I say sublevel, you say shape. Sublevel, sublevel, you're not saying it. When I say sublevel, you say shape. Sublevel, okay, that's better. So just remember, we're talking about the shape of the atom. The f orbitals are really weird looking. You don't need to know the shape. All right, so the number of sublevels is equal to the principal energy level. Now that sounds weird, so just look at the pattern here. When the energy level is level 1, there's 1 sublevel. There's 1 shape, the S shape. But when you get to energy level 2, There's actually two shapes. There's the sphere and the little dumbbell. When you get to energy level 3, there's three shapes. There's the sphere and the dumbbell and the clover. So every time you go to a higher energy level, you add one more sublevel, in other words, one more shape, and so on. So you see the pattern repeating. That will become important when we talk about electron configuration as well. So just tuck that away and know whatever the energy level is, that's how many sublevels, that's how many shapes there are in it. Okay, another thing that's important, the further away you go from the nucleus, the less likely you are to find an electron. They hang out closer to the nucleus. Their density is higher. So the further away, the lower the probability is that you'll find it, because once you get far enough away, they're just not there, because then they're not part of the atom anymore. So density of the electrons decreases as you move away from the nucleus. All right, so electron configuration then is a system we use to map out where all the electrons are in an atom. We can actually say the specific address of each electron in each atom on the periodic table. And you will be able to do this because there's only a few rules, and every single element, every single kind of atom follows these same rules. And here they are. I know you were waiting for this. The Aufbau principle, it's German, it stands for the building up principle. It just means you're going to start with the lowest energy orbital and work your way up. This is good news, because if you're one of those people that's like, I don't know where to start, you can't really say that, because for every element on the periodic table, you always start in the same place. You start at hydrogen element number 1 and you work your way up. So that's super handy. Rule number 2 is called the Pauli exclusion principle, and it basically is, well, it's kind of complicated, but the essence of it is that you can only put 2 electrons in each orbital. When you did the collisions game with the atoms, collision chem thing, and you were like trying to put more in and it wouldn't let you, and it was like full, you had to move to another one, that was because of the Pauli exclusion principle. Those things that you were sticking the electrons into were actually these orbitals that we're talking about right now. So, and they also have to have opposite spin. I'll show you what that looks like later on. If you got 2 in there, it's called paired. If there's 1 in an orbital, it's unpaired. If there's none in an orbital, count them none, then you just say it's empty. There's still an orbital there, whether there's electrons or not. So it's either empty, unpaired, or paired. And the last rule is when you get to equal energy orbitals, they each like to have their own space. So think of this like when you're riding a bus. You get on the bus, you don't know anybody, you look for an empty seat. Everybody looks for an empty seat. Then when all the empty seats are taken and somebody else gets on the bus, they can't have their own seat. They got to go sit with somebody. So, you know, everybody puts their bag in the way and pretends they're asleep or whatever, but it doesn't matter. They got to end up sitting somewhere. This is what electrons do. They each take their own orbital, and then when everybody has their own and all of them are filled with 1 electron, then they start to pair up. So that's what Hund's rule is. We're going to use these 3 rules to figure out the electron configuration of every electron and every element on the table. That's all you need to map them all out. It's going to be pretty exciting. So it's going to look something like this. This is kind of crazy. We'll have to look at some examples, but we'll do that next week. So just kind of review what we talked about here and get super pumped for electron configuration, because it's amazing.